Log on, tune in, find out. Another good idea from Cambridge.
My talk is devoted to inverse source problems of active sound control. Perhaps it's the only one talk on inverse source problems in this workshop. The outline of my talk: I'm going to start from a brief introduction to Calderon-Rabinskis potentials. This technique will be used in the next section, where I'm going to give the formulation of active sound control problem and its links to inverse source problems. Then I'm going to extend the formulation of active sound control problem to composite domains, and some numerical examples and experimental results will be demonstrated. And finally, the summary. So let's consider some domain D, which is a composition of two domains, domain D plus, D minus, and the common boundary gamma. And we assume that all the boundaries are smooth enough. On the domain D plus, we introduce a linear boundary value problem, which is supposed to be well-posed. It's to be noted that the boundary conditions are formulated implicitly in this problem via the following conclusion. We can identify the space Xi D via Sobolev spaces depending on the order of operator L. Details are available in the following my paper. Next, we consider on the domain D plus, we introduce the potential according to the definition. In the definition, V D plus is the restriction of function V to D plus, and G is the Green's function of the problem, and P D plus is the operator. It's to be noted that the Green's function is used for the sake of simplicity in this definition. There is an alternative definition which doesn't exploit Green's function. The key property of this potential is a projection. We can prove straightforward from this definition that this potential is a projection. In a similar way, we can introduce the potential assigning to the domain D minus. Next, following Rabinki, we introduce the notion of a clear trace. First, we consider the following boundary operator, and the clear trace is a pair such that if the clear trace is for two functions Vd plus and Wd plus from the same space coincide with each other, then the appropriate potentials also coincide. It's very important because we can reduce the potential, we can identify the potential via its clear trace. In this way, we can reduce a volume potential to a surface potential. Next, let's consider the formulation of the active sound control problem. Assume that we have sound sources distributed both in D plus and in D minus outside D plus, and we are going to protect domain D plus from noise generated outside. In this way, we consider sound sources situated in D plus as wanted sources, like our conversation, and we have noise outside, so any sources situated outside are interpreted as noise sources. And so the consideration U is the total field from all primary sources, and U plus is the wanted field, provided that all noise sources are switched off. To protect domain D plus, we are going to distribute additional sound sources situated outside D plus. They can be distributed at the boundary of D plus or in the domain D minus. Mathematically, this means we seek the following right-hand side, the following function on the right-hand side is the following property. And we say that function g is a control function provided that the solution to the following boundary value problem coincide with the pure wanted field on D plus. In this way, we have a trivial solution. We have a trivial solution, which is the following. But this solution is so easy to find out, but it's not so easy to realize. Fortunately, the solution to this problem is not unique, and there are more interesting solutions. And we can reduce our problem to an inverse source problem in this way. And we seek the following function, the right-hand side G, satisfying the following properties. What is the input data? The input data is the clear trace of the total primary field from the primary sources. Clear trace of U. The solution to this problem can be obtained via the Calderon dynamics of the potentials. From the property of the potentials, the main property, immediately we obtain the following equalities. And then, if we apply the operator PD plus to the total primary field UD plus, we obtain U minus. So, the potential PD plus is the field in. We can subtract unwanted field from the total field, and then we can kill noise. That is the main idea. A possible control can be obtained by the following function, the right-hand side. The following control. Here, theta d plus is a characteristic function of the domain D plus. It's equal to 1 on D plus, and it's equal to 0 outside D plus. It's easy to see that the support of this function belongs to the boundary gamma. We can obtain the general solution to the inverse source problem, which is the following. But most of the solution doesn't seem too practical, because the support of this function can belong to D minus, and it's much easier to distribute control sources at the boundary of the boundary gamma. Therefore, in our further consideration, we're going to consider only simple layer controls. As an example of this control, let's consider a system of first-order equations. So the details I wrote on this paper. First-order equations with the following matrices as the Cartesian coordinate system. Particularly, you can consider acoustic equations, order equations. Then a simple layer control is given by the following function. N is the outward normal to the boundary. Well, this solution demonstrates a solution is not always practical, because in this solution we require the total field from the primary sources, but in practice our measurement at the boundary can be affected by the control. And this solution can be modified to take into account the reverse effect of the controls. Then the solution can be obtained in the following form. In this case, V gamma minus is the total field from both primary sources and secondary sources, measured at the outward side of the boundary gamma. But this control is non-local, because the potential is non-local. Now let's consider the formulation of active control problem for composite domains. Assume that domain D plus is a composition of two subdomains d plus 1 and d plus 2, and these subdomains don't intersect. Okay? And the field with control is given by the following function. In this case, we introduce two coefficients, alpha 1 and alpha 2. It's easy to see that if both coefficients are equal to 1, then we arrive at the previous formulation of the problem. But our domain D plus is a multiple domain. In turn, if, for example, coefficient alpha 1 equals 1, but coefficient alpha 2 equals 0, in this case, domain region 1 can have region 2, but not vice versa. And in this case, we arrive at a selective control. What is the input data? One can show that the input data are given by the following clear traces. But the wanted field can be obtained via the potentials. But the potentials assigned to the external domain, subdomains. Eventually, we arrive at the following input data, the clear trace of U, but assigned to the external, to the potential on the external subdomain, D minus. In contrast to the previous case, to realize this control, we have to solve auxiliary boundary value problems to identify the clear trace. And this formulation can be extended to an arbitrary number of regions. For example, in this case, region 1 can have region 2, and vice versa. Region 1 can have region 3, but not vice versa. Region 2 doesn't have region 3, and vice versa, and so on. What is the field with the control? The field with the control can be represented by the following vector. Here, M is a control matrix. Its elements are the following. If region I has region J, then this element equals 0. Otherwise, this element equals 1. Obviously, this matrix is not symmetrical in the general case, and all elements at the main diagonal are equal to 0, because each region can have itself. What is the input data? The input data are obtained via the following clear trace, and again, U plus can be obtained via the potentials, and eventually we arrive at the following formulation that the input data are given by the clear trace assigned to the external subdomain. Again, we need to solve additional boundary value problems to identify the clear trace. Details are available on these papers. Now let's consider a few examples. Assume that we have a domain D plus, which is a composition of two cubes, cube 1 and cube 2. And assume that we have a sound source situated in cube 1 at the center of cube 1, and we have a receiver in cube 2. In addition, we have the source of noise situated at the center of the main cube. The parameters of the sound source and noise source are the following. So this is amplitude. And then, so we consider the results as the following plane. The problem is three-dimensional order. In this figure, you can see the distribution of noise. The source of noise is situated at the center. And then we implement the controls. We implement the controls. and this is the area of the first cube, cube 1, and this is the area of cube 2, and we see noise attenuation. In addition, now let's consider the wanted sound. So the source is situated at cube 1. This is the field of wanted sound. Next, we implement noise, and the flow field is significantly damaged by noise. So we have total field for noise and wanted sound. And next, we implement the controls. We implement the controls, and we see that the flow field in cube 1, the wanted sound in cube 1 and cube 2 in the receiver is restored. I see a potential application of this technique to seismic problems when we have noise from the medium, surrounding medium, and we need to filter noise from the measurement data, especially low frequency noise. So if we compare wanted sound in cube 1 and cube 2, so we see pretty similar. Now let's consider another example, similar parameters, but the results are represented by via contour plots. This is the field of wanted sound, the area of cube 1, and this is the area of cube 2 of the receiver. Then we implement noise, and we see the total field, the wanted sound is significantly damaged by noise, situated, so the source of noise situated at this point. And next we implement the control, and the flow field is restored in the area of cube 1 and the area of cube 2. This is the area of cube 1, and the flow field is pretty close to the wanted sound, original wanted sound. If you consider the area of cube 2, the flow field, the total flow field, is pretty close to the original wanted sound, apart from some boundary layer. Next, let's consider some results related to experimental implementation. These results we obtained in collaboration with Salford University, with the acoustic center led by Professor Lam. First, we considered noise attenuation in a pipe. We have a source of noise on the right-hand side, and we protect half a pipe from the noise generated on the right-hand side. The secondary sources are represented by a monopole and a dipole mounted at the center of the pipe. In this figure, we can see the distribution of the sound pressure. In the case of noise, we don't have any wanted sound, we have only noise. And this is the distribution of sound pressure along the pipe for 350 Hertz. The squares correspond to the noise, and triangles correspond to the field with control. And we have quite significant noise attenuation because we have logarithmic scale. Next, we can consider the noise attenuation for other frequencies. So the noise attenuation varies between 20 decibel and 35 decibel. So it's about 95% of noise attenuation. Then we considered wanted sound on the left-hand side. So we have a source of wanted sound on the left-hand side, and we have noise on the right-hand side. Circles correspond to the wanted sound, And squares corresponds to the field with noise, so wanted sound and noise. And we see that the flow field is significantly damaged by the noise. And next we implement the controls and we obtain the following field. The triangles correspond to the field with controls. So the circles represent the wanted field, and triangles represent the field distorted by controls. And the flow field is pretty close. Then we considered noise attenuation for broadband spectrum, and on average, as you can see, the noise attenuation is about 20 decibel. And we considered the range up to 1 kilohertz frequencies. And finally, we considered noise attenuation in composite domains. So we have a pipe, and we split the pipe into 3 sections, 3 parts, part 1, part 2, and part 3. And part 1 communicates with part 3. And we have unknown source of noise somewhere in part 2. In this case, we implement 2 controls. One controls the boundary between domains 1 and 2, and another control between the boundary between regions 2 and 3. This is the experimental rig. So this is region 1, this is region 2 with noise, and this is the region 3. Circles correspond to the wanted field, wanted sound. Okay. And then if we implement noise, we can see the diamonds, and we see there is a very significant difference between wanted field and field with noise. And next we implement the control pluses, and pluses are much closer to the circles. If you consider distribution with respect to different frequencies, circles on the left-hand side we can see the circles, and asterisks correspond to the noise field. We don't need, for our solution, don't need pure noise, we don't need this information, but we can demonstrate. So we see that the level of noise is significantly higher than the level of wanted sound. And then if we implement noise, we see the crosses, wanted field and unwanted field. So the total field from primary sources is much closer to the unwanted field. And next, we implement the controls, and we obtain the solution represented by the triangles. So the triangles are much closer to the circles. On the right-hand side, we can see the error in the restoration of the wanted sound as a function of the difference between the wanted sound and unwanted sound. And the error is pretty low unless unwanted field exceeds the wanted field as much as 10 decibel. Finally, the conclusions. The obtained active control solution requires only the total field at the boundary of the protected domain. It's applicable to bounded regions. Wanted sound can be retained in the protected domain. Green's function is not required in the solution. And this solution is applicable to composite regions. And some references. Thank you for your attention.
Any questions?
Am I right in thinking that only a single microphone between the different regions inside the pipe was necessary to carry out the isolation?
You mean for the measurements or for the control?
For the control.
For the control. For the control, we need a monopole and dipole.
Okay. But not nothing that spans the pipe.
No, only the boundary.
Yeah.
That is the key point. Of course, if we have a composite region, then we have two boundaries. And consider the pipe.
I'm trying to imagine your simulation was like rooms, you know, in a building, and then your control would have to be on the walls. Is there some physical way of doing that? I mean, in your pipe it seemed easier because it was just a plane, but can you put sources all over walls to cancel sound?
Yes, definitely. We can. But of course, we are not able to provide continuous distribution for the sources. In this case, we have to approximate our certain delta function via point delta function, but it can be done.
So it's like covering the wall with loudspeakers.
Yes, of course.
Okay, and that works. Is
Yes,
that's thinking.
even in Stanford University, we started three-dimensional experiments already for a cube. And in this case, there is another problem on optimization of the sound sources because we want to have as many sources as possible with the maximum effect.
But that appears like a distribution of point sources really on the wall.
Yes.
So you're presumably just makes your boundary layer bigger. But if you only have point sources on the wall, then near the wall, the cancellation is not so good, right?
Yes, I demonstrated in computational results. We have this effect. So in Cube 2, for the receiver, we have noise attenuation pretty well apart from some boundary layer. We have this effect.
Thank you very much. In that
Thank
case.
you.